Hello everyone. So today I will be going to perform a virtual lab using spectrophotometer. On the first page, there is some useful information how to handle the system. Uh, so let's start with our first activity: a relation between absorbance and concentration. First of all, we need to fill a cuvette with 3 ml of water and put it into the spectrophotometer and set its wavelength to 405 nanometer, and then we need to make the absorbance is equal to 0, and then take the cuvette out and pour it off. This will be our first thing. So this is 1 ml, and a cuvette can hold only 3 ml of water, 3 ml of a solution. It's ready. So let's calibrate the system first at 405 nanometer. So the system is calibrated. Then we need to take the PNA volume. Let us have it 1 ml first. On the second one, let us take 2 ml. And the third one, 3 ml. And in the first one, take 2 ml of water. And on the second one, take 1 ml of water. Now let us write first. So we have taken in the first cuvette 1 volume of PNF, 2 volume of PNF in the second one, and 3 ml of PNF in the third one. On the other hand, water volume is 2 ml, there is 1 ml, and there is no water present. Once the 3 mixtures are prepared in 3 cuvettes, put them after one by one. This spectrophotometer. So let's see its absorbance. It's showing 0.528. So let's write it. 0.528. What about the second one? It's showing it's more or less half. It's more or less 2 times the first one. It's showing 1.069. Okay, let's take it out and get the third cuvette inside of it. It's showing 1.595. Okay, 0.595. So we can see that as the concentration increases, as the concentration of the pan-nitrophenol increases, the absorbance also simultaneously increases. So yes, they are directly proportional. The absorbance is directly proportional to the PNF concentration. It's about the qualitative one. Let's talk about the quantitative analysis of it. So since we have taken 1 volume of 1 ml of PNF and 2 ml of water. So the uh, PNF concentration is one third of it, of the solution. If the concentration is 80 micromolar, then on the first cuvette it will be one third of 80 micromolar. So one third of 80 micromolar is 26.67. I have the calculator here in my hand, and for the second cuvette, the volume of PNF is uh, two times the first one. So it will be into 2, 53.33. On the third cuvette, there is no water, only PNF present, so it would remain as 80. Let's check out the absorbance at 405 nanometer. So for the first one is 0.528, next one is 1.069, oh, sorry, 1.069, and third one is 1.595. Okay, so calculate the PNF concentration in final mixture of each cuvette, knowing the concentration of etc. Prepare a table with the data and draw a graph plotting A versus C. Okay, so I have taken all the measured values from there and pasted here so as to draw a graph from it. Okay, so the here it will be absorbance on the y-axis, and on the x-axis it will be the concentration. We can so by the graph we observe that it's for a straight line curve graph, it's directly proportional. Higher the concentration of PNF, higher is its absorbance. So it is there is activity 2, the fundamentals of protein quantitation assay. Here we are going to use the Bradford's reagent with the protein for its quantification. So let us first calibrate the system, this system, just like the previous one. So here we are, instead of taking the PNF, we are going to take the Bradford's reagent and fill the cuvette until 3 ml. Now let us calibrate it with at 595 nanometer, and absorbance let us make it 0. So in here let us take the protein volume, be here 0, and the second one let us take it 1, third one let us take it 2. As a result, the volume of reagent will be here 3, here 2, and here 1. So our first cavity is ready with 3 ml of reagent with no protein inside. On the second one, let us take the Bradford's reagent again, and I am going to fill it till 2 ml. The third one, only 1 ml. Now we are going to use the protein. The second one, that is only 1 ml. and for the okay, somehow it's okay. Let us fill it till this and 1 ml in the second one. Just as written it here. So now let's check the absorbance first. Uh, did it change anything or not? Yes, it changed. It changed to minus 0.011. Let's check the second one is showing 0.169. Okay, it's increasing. Third one, let's see. I think it should also increase. Yes, it is increasing. So it will be 0.360. Okay, so the qualitative analysis of the results observe the relation between the color of the covert and the absorbance. Okay, so uh, with as the reagent, as the protein increases, the concentration of protein increases, the absorbance also increases. So this is the relation between this. Yes, there can you observe any dependence about the between the absorbance and the higher or lower concentration of protein. Higher the protein concentration, higher is its absorbance. Now we can see it for the first cover. There was zero protein, zero amount of protein, zero amount of protein. So it was showing very less, that is beyond zero. When 1 ml of protein was added, it was a little bit positive. When 2 ml of it was added, it was a little bit more positive. So yes, it is increasing. Talking about the quantitative analysis of the results, so the concentration protein in the firing machine of each cover is 800 meg per ml, meg per liter, mg per liter. So um, of course, for the first one, the concentration will be 0 because there was no protein inside. The second one, there was 1 ml of protein out of 3 ml 3 ml of solution. So it will be one third of 800. So 800 divided by 3 is equal to 266.67. Similarly, it's 2 by third, so it will be I think 530. Yeah, 533.33. For the first one, it's showing minus 0.011 is 0.169 and it's 0.360. I have taken all the measured values from there and have pasted here so that I can draw a graph by it. So it's the graph and we have the data levels and the axis titles. Here it will be um, it will be the absorbance. It will be the absorbance, and in the x-axis it will be the concentration. Okay. Now, sorry. Now the trend line. Since the intercept value is at minus 0.011. So I'm going to give it minus 0.011. It will minus negative. So okay, it's done. Let's show it here. So it is a straight line. It's a straight line curve, and so we can see that the absorbance is directly proportional to the concentration. The higher the concentration of the protein, the higher will be its absorbance. So here it is given that 1 ml of an unknown sample is mixed with the Bradford's reagent for a total volume of 3 ml. Calculate the protein concentration of the original sample if the assay has rendered a value of uh, a let's reveal it 0.718. Okay, and we have to calculate concentration. Okay, fine. Uh, so it's given that the absorbance, right? I think yes, the absorbance is 0.718. Okay, absorbance means the y is equal to 0.718. We don't know x. We need to calculate here, and we can also check it if it's correct or not. Um, and this is the equation of it. This is a straight line equation. Again, y is equal to, let us write also, 0.0007 x minus 0.011. So it will be, so we need to find the value of x. So x is equal to, it will be y plus 0.011 whole divided by 0.0007. Okay, so let us calculate it. The value of y is 0.718 plus 0.011 whole divided by 0.00007. Value is x is equal to 1041.4243. Okay, so this is the value of x. That means this is the concentration value. Let us see whether is it or not. Okay, control C, copied that, and now paste it. Let's check. I don't know why it's incorrect showing. Let us cross check once more. This will be, I don't think it's 44. So I don't know why it's showing incorrect, but the method is the right one is the correct one. This is how you should take the value of consider the value of y, and then using this information and all this equation, we need to find the value of the x. So I don't know whether it's a technical glitch or something. It is showing incorrect. It must be the correct one. Anyways, going to the second part of activity 2. It's is more or less this same before, like, and the difference is that here we are going to work with three uh, reagents, one with protein, one with water, and another with the uh, Bradford reagent. So, and in this case, the Bradford reagent is 3 times concentrated also. So let us take. So first of all, let's remove all the chemicals and switch it off and switch it on again. Okay. So we are taking the Bradford reagent in this one, the first cover. Let us see. There's 3 ml of water. 3 ml of there's 3 ml of Bradford reagent, and let us take it inside and calibrate it first. So it's 595 only. Let's calibrate it at a is equal to 0. So the first one, it will be let us take the volume of protein be 0. It will be 1. It will be so it will be 2. For the second covered, the protein concentration will be 1 ml. Volume of water will be 1 ml. Volume of reagent will be 1 ml. For the third covered, let us take the protein volume 2, and the volume of water is, let us take 0 here, and the reagent be 1. Okay, so okay. First wait, so let us check it 0, and the volume of reagent, let us take 3 ml, and this one is okay. Yeah. So here is our first cover filled with 3 ml of Bradford reagent. On our second one, there will be 1 ml of each reagent, water and protein. It's water, and then last of all is protein. On third one, there will be protein 2 ml and the volume of reagent 1 ml. Okay. So chemicals are done. Just calculate now. It's showing 0.04 absorbance. In the second one, let us see. Is showing 0.043. Okay. Let us check. third one is great rise. Okay, it's 0.377. Okay, let's take it out, and now let's compare. Um, observe the relation between the color in the covers and the absorbance when comparing the measurements. Can you observe any dependence between absorbance and the higher or lower the concentration of proteins in the cover? So the yeah, there is a relation, and we can see the color changes considerably with the changing amount and the considerable change of the concentration of protein. So in the first cuvette there is no protein at all. In the second cuvette there is a little bit protein that induces a change, and in third cuvette there is uh, 2 ml of protein that changes the color a lot. So the absorbance also increases. So we can say that as the concentration of protein increases, the absorbance also increases. This is the qualitative analysis. Coming to the quantitative one, the calculate the concentration of proteins in the final mixture of each cuvette, knowing that the concentration of the bottle is 800 mg per liter. Okay, that means that the total volume of the total concentration, the actual concentration of a bottle of protein, that means this one, it consists of the concentration is 800 mg per liter. So the first one there is it will be 0 because uh, there is no protein at all, of course. On the second one there it is one third, so it will be one third of 800, and one third of 800 is equal to I have calculated right now, it's 266.67. The third one is showing that 2/3. Okay, there is no water, so it's not taken into consideration. So 2/3 of means 533.33. Let us write the absorbance taken for each of the covert 0.004, 0.043 is 0.377. Okay. Although the absorbance at 595 nanometer is directly proportional to the protein concentration, if we consider the change between the first and the second cuvette, the rise of the absorbance is not as much when compared to the difference of second one and to the third one. So, if you draw a curve, here is our measured values. If I press it from here to here, so let us make a graph and let's see. Okay. Mm, so this was at the time when the concentration was 0, but the absorbance, so the absorbance was at 0.004. When the concentration increased to around 266.67, the absorbance rose a little bit, but if when crossed over 500, when it was around 533.33, there was a major difference between the second one and the third one. It was a huge rise compared to the first low. So um, this is about the second part of the second experiment. So this is our third experiment, third activity, the absorption spectrum of hemoglobin. Here, using the water and hemoglobin solution, we are going to prepare different dilutions and analyze their UV spectrum. So first of all, let us remove the chemical mix, and then um, the first one. Okay, let's take here 3 ml, here 2 ml, and here 1 ml. So there is 0, here is 1, and here is 2. So we are going to take 3 ml of hemoglobin in the first cuvette. So let us take it and pour it. So there is one, there is the second one, and there is also 3 ml. The second one we are going to put 2 ml of it, and the third one we are going to give only 1 ml. And for the first one we are not going to give any water. So, and in the second one we are going to take 1 ml of water, and the third one we are going to take we are going to take 2 ml of water. So now let us consider this one, put it inside the spectrophotometer, and um, click the record button. Okay, let's record it. Okay, so let us snip the this one, and in here I'm going to paste it. This is for um the first cover. Okay, I've written it one here. Similarly, I'm going to separate for the second and the third one also. Here is the third one. Yes, I'm sorry, here is the second one, and let us take the third one also. Okay. And it's for the third one. So if we see Yeah, uh, um, we can clearly see that the maximum absorbance is at 420 nanometer around. Each of them are around 420, 415 to 420 nanometer. The absorbance, the peak of its absorbance lies around this region. So um, we can say that if we consider that from in the first cover there was 3 ml of hemoglobin, and in the second cover there was 2 ml, and in the third cover it was 1 ml. So in the first cover there was 3 ml, in the second cover there was 2, and the third there was 1. So we can see that the higher the amount of the concentration of hemoglobin, higher is its absorbance. We can say that. So um, it has so it is given that the actual concentration of the hemoglobin bottle was 200 megs per liter. So in the first cover there was only hemoglobin, no water. So that means it is pure hemoglobin and its full concentration 200. It was two-third. It was given 2 ml and 1 ml was of water. So it will be two-third of the 200 ml. That means 133.33. Similarly, in the um, third one, there was only one volume of hemoglobin and two volume of 2 ml of water. So it will be half of it, 66.67. So let us okay, okay. So we need to find the maximum um, the lambda where there was the maximum absorbance. So let us first calculate with this also. This first, it was around 400 and 415, like that, 420 round. So let us see what was around 400. Okay, we can see that the absorbance is still rising. It is still rising at 416. Oh, it is still rising at 416. Just wait a second. 700. Okay, so um what happened? Yeah, I'm sorry. So it is rising at 413, 414, 415. Okay. Okay, the maximum value is 415. Yeah, the the value of the maximum value of A remains at 415 nanometer. So the wavelength is 415 nanometer. Let us first also see the other one also. What was like okay, 15 1.226 at okay, 414, 415 is 43, 416. Okay, 415 also here. Yeah, 415 too. Let's check out for the first one. It's 1778 for at 450 nanometer. 1773. It decreased. Wait a minute, no, it increased at 416. 65. 165. Yeah, it's increasing. It's nearly about 415 nanometer. So it's okay if we write 415 nanometer. 415 nanometer. Oh, okay. We can. We need to let us write this. For the first cavity, it's 1.767. For the it's for the second one, it's 1.231. For the third one, let's see. Sorry, I was a bit too fast. Okay, it was okay. Fine. 0.687.